Hello everyone, and welcome back to Chapter 4. I have been having some issues with my microphone producing some static. Hopefully I've gotten most of that cleared up, but I won't know for sure until after I have completed this video how bad it is. So I apologize in advance if there's too much background static. But for this video, we're going to spend our time going over a couple of example problems using the two-dimensional kinematics, and then when we come back for the third and fourth videos for this chapter, we'll move on to some different topics. So for right now, in Chapter 4, the previous video we saw an example problem where we threw a rock off of the top of a cliff, and then we used the kinematics both in the x and the y directions to show us how we could solve for the system by breaking this two-dimensional problem into two one-dimensional problems. And by doing that, it really does help to simplify and keep things organized, even though it might look like we're doing twice as much work. Just by keeping things organized, I think it's really more efficient than trying to tackle everything at once. So what we're going to do with the next example problem here is, instead of just pushing that rock off of the top of a cliff, we will launch it from a catapult or a trebuchet or a cannon, whatever device that you want to use. And as we launch that rock, there will be a certain initial velocity vector and an initial angle in which we launch the rock, and we're going to assume that everything occurs over a flat horizontal field, and so we will land at the same vertical height as what we were launched. So when we get over here and we have our final velocity vector, there will be a final angle associated with that. But then there's everything in between. And there are a lot of questions that we can ask about this system. And so I'm going to start making a list of things that we might want to know. Given some initial information, we'll say that the initial velocity of our payload here, whatever it is, if it's a cannonball or a rock, we'll let that be 100 meters per second. And the initial angle at which we launch, we'll let that be 30 degrees. So from there, all of the other things that I would like to know, specifically I would like to know what is the final velocity of the payload when it strikes the ground. What is that final angle? I would like to know the total time of flight from launch to impact. I would like to know the total displacement along the horizontal direction. So what I'm going to do is I'm going to assign a reference frame right now. So everything to the right will be positive along the x direction, and everything pointing up will be positive in the y direction. Now I know that we've seen previous problems where we let the the vertical axes point down, but if you notice, during certain parts of the flight, we have velocities and displacements that are pointing up, but then during other portions of the flight, we have velocities and displacements that are pointing down. So it's really not going to matter whether we let up or down be the positive y direction, because something somewhere within the system is going to have to be negative eventually. And so what is the total y displacement? And that we should be able to answer right now. That's going to be 0. And that's because as we've gone all the way through this flight, we have started and ended at the same vertical height. So the change in the vertical position is 0 for the total flight. But more importantly, what I would like to know is what is the maximum height? As this payload is flying through the air, it will eventually reach some maximum height before it starts to descend, and I would like to know what that height is. Now, the way I've drawn this, it looks as if that maximum height is going to occur halfway through the flight. But we don't want to make any assumptions just yet. So what I'm going to do is I'm going to segment the displacement delta x into two pieces. I'll say that there's a displacement during the first portion of the flight, and there is a displacement during the second portion of the flight. I'm specifically avoiding using the term half. I don't want to say the first half or the second half because that implies inequality. And I don't know that these displacements are equal just yet. All I know for sure is that whatever the combination of the two, that will have to equal the total displacement. The maximum height, well, that's going to equal the total displacement in the y direction for that first segment of the flight. But then the payload will have to fall back down the exact same amount, just in a different direction, because we know that the total y displacement will have to be 0. So if delta y1 plus delta y2 combine to make 0, then delta y1 will have to equal the negative value of delta y2, and that's exactly what we expect for the cannonball flying up to a maximum height and then falling back down again. So if the total displacement along the x direction can be broken up, and if we can account for it using delta x1 and delta x2, well, then I would like to know what those values are. Likewise, I would like to know how much time is required for the cannonball to reach the maximum height, and then how much time is required for it to fall back to the ground. Just like the displacement expression, the combination of the times we'll have to add together to equal the total time of flight. And so that means we can take our total time of flight and we can break that up into T1 and T2. And let's see what else that we can solve for. I would also like to know what is the magnitude of the velocity at the maximum height. Okay. So there is a lot of stuff here, granted, but keep in mind that quite a bit of this stuff is interrelated. We have the total displacement in the x direction, which is just a combination of the individual two values. We've got the total time, which will be a combination of the times, and then the maximum height and the total displacement. Those are related by the fact that we know that we're starting and ending at the same vertical height. All right, so what we need to do now is we need to go through this list that we've made of things that we want to find, and we need to ask ourselves, where do these values occur? Because some of these values are going to depend on information from the initial starting point of the problem. And what I mean by that is right here there is some initial information about what is happening in the problem. We have x and y components of the initial velocity vector that we could solve for and then use in a kinematic equation. Likewise, there are x and y components of the final velocity that we are going to want to solve for, so that we can put those together and find the information about the final velocity. And so right there, we can use some trigonometry with the vectors. But then there's also quite a bit of stuff that's occurring right up here. Specifically the maximum height, the time t1 that it takes to reach that maximum height, and that time t1 is going to in turn relate to how far we can travel along the x direction during that time interval. And so what I need to do is I need to set up my kinematic equations with respect to these three different locations. I have an initial location, I have a max height, and I have a final location. There's three different locations where I can apply the mathematics. And the kinematics, let's say we take this kinematic equation right here. This kinematic equation says I have to relate the initial velocity to the final velocity. Well, these subscripts really just mean that I have to relate the velocity of a starting point to some end point. I could start at point 1 and end up at point 3, but I could also start at point 1 and end up at point 2. In other words, I can compare the information at any two locations using this kinematics. I don't have to go all the way from the start of the problem to the end of the problem. I can segment this pretty much as many times as I want, so that we can step our way through the problem chronologically and see what's happening. And so that's what we're going to do. I'm going to start with all of that initial information of V naught. So we're going to start at the initial launch, and we'll go to the max height and see what information is there. Now we do have X and Y directions in this problem set, and I'm going to remove some of this stuff so that things don't get too crowded. There we go. I think that's a little better. And what I need to do now is I need to figure out what are the X and Y components of the initial velocity. I'm going to call the velocity up at the maximum height V1. And so V1 will have some components. We will have the acceleration of the system. We will have the displacements. And we will have the times. Now, more specifically, the displacement that occurs from the starting point to the maximum height along the x direction is delta x1. That is one of the values that we're searching for. And the displacement that occurs along the y-axis is delta y1, also known as the maximum height. The velocity components v naught x and v naught y, well, let's take a look at those. V naught is 100 meters per second, and we have it angled at 30 degrees right over there to the right. Those were the values that we were given. And so we're going to use those to find the components for the x and y directions. We have magnitude of 100. The x component is the side that is adjacent to the angle, so that is cosine 30. Put in 30 there. And then the y component is the side that is opposite of the angle, and so that is going to be sine of 30. We'll get out our calculator. 100 sine 30 is just going to be 50. And 100 cosine 30, I want to say that that is about 87. But I'm going to plug this into the calculator just to make sure. I'm going to open up my calculator app here. Here we go. 100 cosine of 30 is 86.6 meters per second. Next, we have the components of V1. So we're looking for the components of the velocity when the payload gets up to the maximum height. Well, the reason we call that the maximum height is because it doesn't go any higher. And that means that momentarily the ball will have a velocity of 0 in the y direction. And the only velocity component that is left will be in the x direction. So we can say that the y component of our velocity up at the maximum height is 0. but there's still going to be an x component over here somewhere. I'm not exactly sure what that's going to be, so we might want to leave that alone for right now until we do get some more information. So we'll step down to the accelerations in each direction. And we said in the previous video we are not going to consider air resistance, and so until further notice we can allow the acceleration in the x direction to be 0. And the moment we realize that, we can come back and fill in the value for the x component of the velocity at the maximum height, because if we're not accelerating in the x direction, then our velocity along the x direction cannot change. So we have to have the same values there. The acceleration along the y direction, well, in that case we have gravity, but gravity is pointing in the direction that is opposite of what we have designated to be the positive direction. So I do need to use a minus sign here. And then the time, well, in this case the time that we're looking for is t1. Those are the same values for both the x and the y direction. So if anything, if we can solve for the time in one column, we can move it over and share it in the other column, which is what we're going to have to do, because right now in the x direction I have that one situation that doesn't work. I have that one case scenario where the kinematics is not going to work out, and so we will need to solve for the time, and that means we're going to have to focus our attention on the y-axis for right now. But that's okay, because in the y-axis I do have 3 independent pieces of information that I can use to solve for the other 2. And that's exactly what we're going to do. I'll start with the maximum height. I want to solve for the maximum height, and I want to use the given information, which means I need a kinematic equation that leaves out time. We go back to our chart of kinematic equations. The one that leaves out time is this one. And remember, we are only working in the y direction right now, so I'm using y displacement. In fact, every value that I plug into this equation is going to come from the y column. Now we're trying to solve for delta y, so I will take this expression and rearrange it to solve for delta y. Then we'll plug in our numbers. The final velocity in the y direction, well, that's going to be the y component of v1, and I just now realized I had an x there. Sorry about that. That should be a y. We have final velocity of 0. We have initial of 50 over 2 and negative 9.8. The displacement of this cannonball, or whatever it is, as we see, delta y1 has to be pointing up, and up is the positive direction for this system, and so the math should also reflect that. We should be getting a positive answer. And if we put everything into our calculator correctly, right up here, keep in mind that you are subtracting the square of 50. You do not have negative 50 squared. Okay, the order of operations says that you need to take care of your powers first, then you can do your subtraction. So up in the numerator, we're going to have 50 squared with a negative sign attached to it, divided by the 2 and the negative 9.8, and that quotient will produce a positive outcome. And that is what we want. And I am getting, let's see here, 127.4 meters for the maximum height. And I'll just double check my answer here. Yep, that looks correct. So we're going to reach a maximum height of 127.4 meters. Pretty high. And we'll bring that up right here. 127.4 meters. Now we will move on to the time of flight, T1. I want to find the time. I again want to use given information. I don't want to use something that was calculated unless I have no other choice. So we are looking for the kinematic equation that does not involve displacement. And that would be this one. We just need to rearrange it to solve for time. And now we can plug our values in. Again, these are only going to be the values from the y column. We have final velocity at the maximum height is 0, initial is 50, acceleration is 9.8, and just like before, careful of your algebra, we have a negative 50 that is being divided by a negative 9.8. And that results in a 5.097, so I'm just going to round that up to 5.1 seconds. So time 1, 5.1 seconds. 5.1 seconds, and likewise 5.1 seconds. And now we have everything that we need to solve for delta x1. I now know the time of flight during that first interval of displacement. There's only room for 2 additional terms in any kinematic equation that we use. I definitely want to use the acceleration because that's a 0. 0 always makes the algebra easier to work with. And then I just have to pick one of the 2, either the initial or the final velocity for this interval. I'll go ahead and pick the initial. So I need an equation that leaves out the final velocity. And that should be this one. And, whoops, not delta x, delta x is already there. We need a t squared. There we go. And now that we're working with the x direction, all of my information will come from this x column. We are already set up to solve for delta x, so we just need to plug in our numbers. Keep in mind the acceleration is 0, so that whole back term is just going to drop out. We have initial velocity component 86.6 and a time of 5.1. We'll multiply those together and we get 441.7 meters for delta x1. 441.7 meters. All right, so that's looks like about a third of all of the values that we were asked to solve for. And so now that we've essentially filled in this entire table of information, what we need to do now is set up a new physics problem. And I have a choice to make now. A lot of the other values that we've been asked to solve for over here are going to occur over here at the final impact site. The total time, the total displacement, the final velocity with its components. But I need something else that I can use to calculate from, and that means I can either go back and use that initial information, or I can use information from the maximum height. Well, what I'm going to do is I'm going to use the information from the initial location because that was given information. There's really no reason I couldn't use the information from the maximum height except that it's calculated. And we know now that if we use calculated material, we run the risk of it being wrong, and then our other answers will be wrong as well. So I'm going to erase all of this, and we're just going to start fresh with our kinematics. I want to compare what is happening at the initial launch site to what is happening at the final impact site. Now, a lot of these values inside the kinematics may be the same, and that's okay. But I want to start fresh, just so we can see exactly what it is that we're using. We're starting over here at the initial launch site, so we will have the same initial velocity components of 86.6 and 50. So that's at least one benefit of starting back at the initial site, is that we already know what those values are going to be. And the final velocity component, when we get to the impact site, along the x direction, well, that should still be 86.6 because the acceleration along the x direction should still be 0. For the y direction, well, I don't really know what that final velocity component is going to be because the acceleration along the y direction was not 0. We're actually going to have to solve for that, but that's okay. We can do that. The other things that we have to consider are the total displacement along the x direction and the total displacement along the y direction. Now, looking at this picture, the path that I've drawn for this cannonball, it does look very symmetric, which is why we would be very tempted to say things like the first half and the second half. Well, if things truly are symmetric, then what does that mean? Well, does it mean that delta x1 and delta x2 are the same? Does it mean that time 1 and time 2 are the same? We knew that the magnitudes of delta y1 and delta y2 are the same. They just happen to be in opposite directions. In one case we were traveling up, and the other we were traveling down. But it does look like there could definitely be some symmetry in this system. It's just our job to prove it. And if we can prove it once, then we don't need to come back and prove it again. If we run into a situation like this in the future, then we can come back and we can just say, oh, remember that time we did the Cannonball Problem and everything worked out to be this way. Well, then we can argue that fact for future problems. And then the last thing that we have inside these columns is going to be the total time of flight, which should again be the same for each. So now we're over here looking for these values. What are we going to do about time 2 and delta x2? Well, if I can get the total time of flight, remember that the total time of flight has to be the combination of the two. And because I already know what time 1 is, if I get total time of flight, I automatically get time 2 for free. Likewise, for the total displacement along the x-axis, I already know what delta x1 is. If I can find the total displacement along the x direction, then I'll get delta x2 for free. So here we go. We'll see if we can do that. What information do we have so far? I once again have that impossible scenario over in the x direction. Constant acceleration and constant velocity. So I won't be able to solve anything in the x direction until I find that total time of flight. But in the y direction, we're lacking some information. Looks like we only have 2 pieces of info over there. But remember that we said the payload was going to be launched and land at the same vertical position, and so our displacement along the y direction is 0, and that is the third piece of information that we need. Let's see. Let's solve for the final y component of velocity. And that means that we're going to use everything except for the time, and so we can actually reuse that equation right there. We need to rearrange for v final, which we almost have. We just need to take a square root of each side. Keeping in mind that the consequence of taking a square root is that our answer could be plus or minus. Looking back at the diagram, looking back at the picture, the final y component is pointing in the negative direction, so we need the negative answer. Time to plug in. We have 50 squared plus 2 times a negative 9.81 times 0, which, well, that makes the whole back portion of that 0. And now we just have the square root of 50 squared, which is going to come out to be 50. So we have a final y component of negative 50 meters per second, whereas the initial y component was positive 50. Oh, that kind of looks like there might be some symmetry hidden in there as well. The initial magnitude of velocity in the y direction traveling up is the same magnitude as what we get when we land. Moving on, now we'll find the time. We probably don't want to use something that was calculated, so we need the equation that leaves out the final velocity. That equation is, let's see, final velocity left out, that equation is the initial t plus 1/2 at squared. That needs to be rearranged for time. Right now that is a quadratic, and unfortunately I don't have an initial velocity that is 0, and I don't have an acceleration that is 0, but I do have a displacement that's equal to 0. So is that of any help? I mean, we still got a quadratic there, but because every term on the right has a t in it, we could factor out a t, and 0 divided by time, whatever that time is still going to be 0. So what's left is not a quadratic equation, and we can solve this. We can take v naught over to the other side, we can multiply it by 2, divide by a, and there's our time. Now you might be a little uncomfortable with that just because of the minus sign that's out there, but let's see what we have for terms to work with. Our initial velocity component was 50, and we have an acceleration of negative 9.8. Okay, so that takes care of itself, which is good, because we can't have a negative time. If we do, we got to go back, check our work, see what went wrong. But here our minus signs are canceling out, and we're getting approximately 10.19 seconds for the total time of flight. But I'm kind of curious as to this part over here. For a quadratic equation, you're technically supposed to have 2 answers, and we only got 1. Well, there is a second answer to this. If we backtrack a little bit in the math that we did, we want this entire expression to equal 0. Well, that could be accomplished if we let the time equal 0. And you might be thinking to yourself, well, you know, we can't let the time equal 0. The ball can't get from the initial position to the final position. You know, we can't make it from over here to over here if there's no travel time. But the kinematics didn't know any better. Remember that here we were only using information from the y-axis. And so what we've asked the kinematics to do is tell us how long it takes for this cannonball to displace itself 0 meters along the y direction. And so the math spits out 0. It says, just don't launch the cannonball, and you'll achieve a displacement in the y direction that is equal to 0. So it does make sense physically. But in terms of being able to move the cannonball in both the x and the y directions, we can't use the 0 as a solution. We have to use the 10.19. Right, so we have a total time of 10.19 seconds. And if we plug that in here, if we have a total time of 10.19 seconds, that has to equal time 1, which is 5.1, plus time 2, which means that time 2 has to be 5.09 seconds, or, you know, given that I probably have a little bit of a rounding error in there, the time for the first segment of our journey is in fact equal to the time of the second segment of our journey. So it does in fact look like we have a symmetric system here. The time up equals the time down. All that's left is to check on the delta x values and see if we get some symmetry out of that. So for our delta x values, now that we have a total time of 10.19 seconds, we can use that in the x direction to solve for the total x displacement. We have a constant velocity of 86.6 meters per second, and we have a time of 10.19 seconds to travel. We multiply those together and we will get the displacement, the total displacement, 882.8 meters. So our total displacement along the x direction, 882.8 meters. 882.8 meters. 882.8 meters has to equal delta x1 plus delta x2. And just like with the time values, given a little bit of a rounding error, delta x1 is equal to delta x2 in terms of their values. So I'm just going to go ahead and sneak an extra value in there. And wow, that is a lot of stuff. That was a lot to answer, but now that we've done this, we don't need to come back and do it again unless there's some major change that has occurred in the system. So we've gone through and we've answered, let's go through and highlight everything that we've got here. We've got the individual times and the total time. We have the individual displacements and the total displacement. We have the maximum height. We got the velocity at the maximum height. The only thing that we haven't done yet is we haven't put our components for the final velocity back together. But take a look at how those components compare to the components of the initial velocity. If you put those back into your Pythagorean theorem, it turns out that the magnitude of the initial velocity is equal to the magnitude of the final velocity. They're both 100 meters per second. The only difference that you're going to find is in the angle, where the initial velocity vector had an angle of positive 30 degrees. Look at the direction that the final velocity vector is pointing. Well, with respect to the x-axis, that would be a negative 30 degrees. But once again, this is showing us the symmetry of the system. The initial and final velocities have the same magnitudes. They have the same magnitude of angle. The times for the first and second half, yes, I can use that word half now because we do have symmetry confirmed. The times are the same. The first and second half of the displacements are the same. So I guess we never have to do a projectile motion problem again. Well, sorry, we will. But now that we have seen this kind of a problem worked out in all of its steps, there's no reason why we can't take a similar problem and adjust it slightly. So now consider that you have a cannon that you're going to fire, and you want to strike a target, like a castle. So you have your initial velocity vector, you have some initial angle theta, and you have your target, which is a certain distance away. Maybe this target is 200 meters away. And we'll say that our initial velocity vector, we'll turn this into a catapult. Maybe it's 50 meters per second instead of the 100. And we'll switch our angle to 60 degrees. So given all of that information, how high above the ground is the payload going to strike the castle? That's what I want to know. Now, granted, there are all other kinds of questions that we could ask, like what's the magnitude of the velocity at impact? What would the maximum height be? Well, these are all things that we can answer as well, but I just want this one answer. That's what this one last example problem will be. How are we going to adjust this for a problem where we do not, in fact, have symmetry, because I am not launching and landing at the same height as what we had in this previous example? Well, let's see what the kinematics says. Let's make ourselves a chart in a table. I do need to set up a reference frame. I'll use the traditional reference frame again. So that means I have initial x and y components of velocity that are both positive. Gravity will be negative. I have an x displacement that is in the positive direction. So let's see what we've got to work with. The initial velocity in the x will be magnitude 50 meters times cosine of 60. And that is 25 meters per second. Initial velocity component for the y direction. Since we've already used cosine, I guess we have to use sine. And that will be 43.3, I believe. Just want to double check because I don't trust my brain to do this trig sometimes. So sine of 60 times 50, yeah, okay, 43.3. For the final components, again, we didn't really ask about those, but we could solve for them if we wanted to. Components of acceleration, until further notice, acceleration in the x is 0, but that means we know what the final component of velocity in the x direction is. It also has to be 25. Acceleration in the y direction is gravity. Gravity is pointing in the negative direction with respect to our defined reference frame. We have our displacements and our times. Now, for this particular problem, the reason that I did not ask for the maximum height is because how do we know for sure? How do we know that this particular catapult is actually going to achieve the maximum height before it hits the castle? even though I've drawn it in a way that looks like it's already crested over its maximum height, it's possible that we could strike the castle while this payload is still ascending. But it's also possible that it could be striking during a descent. But the kinematics doesn't really care. All we want is we want to tell the kinematics how high this payload is when we've reached 200 meters along the x direction. And now if you notice, I've actually got 4 pieces of information along the x direction. And that's more than enough to solve for the time of flight, which is a good thing because I don't have any other information in the y direction to help me. So here we go. In the x direction, we have a constant velocity of 25 meters per second, and I need to know how long it's going to take to travel a displacement of 200 meters. So all I'm doing here is I'm taking the average velocity expression, delta x over delta t equals v, and I am justified in using that because what is the average of a constant value? We're using a constant velocity here. Well, if you just keep using the same value, 25, 25, 25, 25, and then you average it out, well, you get 25. So in solving for the time of flight, we need, let's see here, 8 seconds. 25 times 8 would be 200. So we need 8 seconds for the time of flight. 8 seconds. We now need to apply that to the information in the y column. And we're looking for the height. So we'll go ahead and use the time because we don't have a choice. It may be a calculated value, but it's the only other value that we have, along with the other givens, and so that means we don't care about the final velocity component at the moment. The equation that involves all of those and leaves out the final velocity is delta y equals v naught t plus half a t squared. And since this one is already set up to be solved for y, all we have to do is plug our numbers in. .3 times 8 is 346.4. Then we have half of gravity times 8 squared. And that is going to make for a total displacement of 32.48 meters above the ground. So that is where we strike. I'll round that up to 5. So meters in terms of feet, that's about 100 feet above the ground, so a pretty tall structure there. But now I'm kind of curious. Did we strike this castle on the way up or on the way back down? And you might think that you would need to solve for where the maximum velocity occurs, or not the maximum velocity, excuse me, the maximum height. But in actuality, there's a very quick shortcut that we can take just by solving for the final velocity component. This component, we only have two choices. Either it comes out to be a positive or a negative. If we solve for this and we get a positive velocity, well, that means that we're still moving in the positive direction, and so we're still traveling up. If we're still traveling up, we haven't reached the maximum height yet. But if we solve for this and we get a negative, then it means that we're on the way back down, and we've already passed the maximum height. So this would be a very quick calculation, and we can then confirm whether we've passed that maximum height or not. To do this, we would need the initial velocity component, the acceleration, and the time. So we don't want to use that displacement that we just solved for. Leaving out the displacement, the equation that we need would be this one. This is also set up to be solved for the final velocity. We have initial value of 43.3 plus a negative 9.8 and 8 seconds. Now, I don't even have to plug this into my calculator to know that we're going to get a negative out of this. I know that 9 times 8 is 72, so this right here is actually going to be closer to a negative 80. And so I combine that with the 43, I get a negative number. And so I know that we're already past the maximum height without even having to know what that maximum height is. Now just for the sake of having all of the information available to us, I'm going to plug this into the calculator. And we have a final y component that is equal to negative 35.18 meters per second squared. If we put that information together, let's see, just a moment here. Oh, no, we're fine. Okay. So if we put that information together in our Pythagorean theorem, so square root of the sum of the squares, and then take the square root. The impact velocity of this payload when it hits the castle is only about 43.2 meters per second, whereas when we launched, the velocity was 50 meters per second. So we've lost a little bit of speed by not allowing the payload to continue accelerating under gravity. And this is actually not a good thing for warfare, because the faster the payload goes, the more damage it's going to do. And so what a lot of generals would do is they would actually try to set up their siege engines in such a way that they could get the payload to land at the same vertical height as what it was launched from to maximize the speed. Now, from the from the castle standpoint, you might be asking, well, why would you want to launch just to hit the bottom of the wall? Well, in addition to maximizing the speed of the impact, you also maximize your chances of bringing down the entire wall. So if you were to destroy the foundation of that wall, everything above it would come crumbling down. Whereas if you were targeting somewhere up higher, well, the damage that you do wouldn't really be all that excessive. Alright, so I'm going to go ahead and end the video there. Hopefully the static noise in the background wasn't too bad. And if it's not, I'll continue making future videos. Otherwise, I might have to go and look for another headset with a microphone. But until then, I'll see you at the next video.